Welcome to Learn Robotics and AI. And in this video, I'll be sharing with you the experience of a project manager in the United States who has a background in arts. He did his bachelor's in arts with a minor focus on computer science. Throughout this video, I'll be referring to him as Daniel Caruso. Daniel is 25 years old and he wants to pursue a master's in engineering. Essentially, he wants to transition to an engineering domain from a project management profile, and he is primarily interested in space applications. He wants to transition to robotics engineering, but he wants to gain an exposure to different hardware and software profiles in robotics. So he wants to explore these and he wants to find out his niche within the vast domain of robotics. And he says that he seeks a project based curriculum because he this is how he learns best. He learns best by doing and really participating in hands-on activities and projects. He is very progressive. He wants to keep on making progress, and he is young and he wants to have an impact. He's driven, active, and analytical, and he says he likes working in teams. And he has worked as a tool mechanic for a few months, and he really enjoyed that process of tinkering with cars and electronic components. This is also something that he enjoys doing in his free time. So he likes playing with hardware. He has a particular interest in space technology, and he has a good foundation in mathematics, and he likes to constantly learn new things. He has no financial constraints. He is also open to going for a master's, and he wants to essentially make a transition within a span of 2 to 3 years, and he is open to relocate to another city or even move to another country if that is required. He's willing to spend 2 hours every single day towards his learning goals and 4 to 5 hours on the weekends. That is approximately 20 hours a week. And this is the learning framework that I designed for him. It would first start with creating a plan for a project. So, first of all, we would select a project, and that project would be of interdisciplinary nature and would consist of mechanical, electronics, and software components. So, one single longer project rather than doing a lot of mini projects, as I've talked about in some of the earlier videos. So for this particular scenario, for Daniel, a more interdisciplinary route would be more useful since he wants to explore a lot of different engineering domains and really figure out his niche. So first he has to select a project, first he has to create a plan for the project, and then build the mechanical subsystem, electronic subsystem, and the software or AI subsystem, and then only then can Daniel expect to really identify his niche by really identifying what is the kind of project or what kind of subsystems does he really enjoy working with. And how does one select a project? In order to select a project, you have to create a list of top space robotics companies. Since Daniel is primarily passionate towards making a contribution to the space industry and he wants to explore space robotics, so this is going to be the focus of this video. I'll be sharing a list of top space robotics companies and how you can really define projects based on your own applications of interest, in this case space robotics. So create a list of top space robotics companies and then extract the skills and the tools from the job requirements of the companies. You can visit the official websites of these space robotics companies and really try to filter out and find and extract the skills and the tools that those companies require for different positions. So mechanical engineering positions, for software engineering positions, and also for electronics roles. And you can check out their primary products and services, the kind of products that they are working on, they are building, or the services that they're providing. And you have to create a list of projects that you find most interesting, that are more relevant towards your career goals, and you have to create simplified versions of the project. So you create a list of projects that would be miniaturized versions of real world space robotics projects, and then select project based on interest but also on feasibility. The project should be doable within a specified time span. So here are some space robotics companies. Um, these can be categorized into a few categories, such as space exploration and launch services, and these are the companies that everyone knows about: NASA, SpaceX, Blue Origin, Firefly Aerospace, Northrop Grumman Corporation, Spin Launch. And when it comes to space stations and habitats, then there's Axiom Space. For satellite manufacturing and servicing, these are a few companies: Lockheed Martin, Terran, Orbital, Ball Aerospace, Ursa Major, Pixel, Maxar Technologies, Altius, and Capella Space. These are some companies there, and the companies that would be most interesting for Daniel are these companies that deal with space robotics and automation, and those include Oleus Robotics, Honeybee Robotics, Motive Space Systems, Made in Space, which is now part of Redwire Space, and Astrobotic Technology. There are also some companies that specifically target software and data analytics for space operations, and one of these is Epsilon 3. And a company that focuses specifically on offering propulsion systems is Benchmark Space Systems. So we'll be specifically focusing on companies that are in the domain of space robotics and automation. So these are the few companies that are listed. And other companies that might also be of interest are those dealing with satellite manufacturing and services, since these also require automation and robotics to a certain extent. So, for the sake of simplicity, I would like to broadly classify the category, companies in the category of space robotics and automation into servicing, assembly, and manufacturing. So, the ones that deal with servicing, manufacturing, and assembly, and space exploration. So, this is a very broad categorization. And of course, this can be split further into a lot of different subcategories, but these are two primary categories I'm considering for the sake of simplicity and really exploring this overall domain. So, servicing, assembly, and manufacturing. So these are a few systems that a lot of that the company that a few of the companies that I mentioned um, create. So X-Link is a robotic arm by Motive Space Systems, and then Spider is also essentially an extension robotic arm system that can be assembled onto another system on a satellite based system. So this is by Maxar. And then another technology is that of 3D printing in space using a robotic arm. So Arkinaut 3D printer by Redwire Space. So these are some companies or some sort of products that space robotics companies offer in the domain of servicing, assembly, and manufacturing. Of course, there can be a lot of different um, other sorts of products, but these are some products to name a few. And there are some other products in the essentially in the space of space exploration, and those include the Peregrine lander by Astrobotics, Sampler by Maxar, and Planetary Deep Drill by Honeybee Robotics. So these are a few category of robotics, and the reason why I'm sharing these is that the projects that I have defined for Daniel essentially would be derived from these real world projects. So those would be miniaturized or simplified versions of these existing real world industrial projects. So one is a miniature robotic arm for sample collection. So the project statement goes like this: you have to build a small scale robotic arm which is capable of picking up and storing samples, and this is essentially part of exploring space. So on the surfaces of Moon and Mars, one essentially needs to really collect a lot of soil samples, and so that one can understand the texture and quality, and one can really do an analysis on these samples. So the goal is to develop a 3 degree of freedom robotic arm, again a simplified version of what an actual project might look like. that can autonomously collect and store up to 5 different samples, and the project difficulty level essentially for most of these would be 3 or more, because it involves mechanical, electronics, electrical components and software, and maybe even AI and machine learning for some of the components, which can be moderately challenging, but it is essentially doable, because I'll be sharing a yearly, monthly, quarterly plan after I'm done sharing the projects. So this is how the mechanical subsystem would require to look like. So you have to design and build a 3 degree of freedom robotic arm with a gripper essentially for sample collection. And this picture is essentially a dummy picture. The project that you build may or may not look like this. You can also really narrow down or cut off some of the components depending on your interest, and once you start figuring out your interest as you start doing your project. So the tools that would be of use for this project are SolidWorks or CATIA or any other design software. SolidWorks is easy to start with, so SolidWorks is something you can really begin with, and then CNC machining is essentially one other tool that you might need to use for this project. You need to know concepts in mechanical design and kinematics and dynamics, and you need to understand materials, screws and bolts, just some basic mechanics. And since Daniel has already worked in uh, essentially servicing of automotive components for a few months, he's used to doing hands-on work. So this is something that he just probably needs to understand some of the theoretical mechanical engineering concepts and not really go into too much details, and really focus on building and tinkering the mechanical subsystem. Then comes the electronics or electrical subsystem, which includes integration of servo motors for the arm movement and sensors for object detection. And you can use tools like LabVIEW and oscilloscope. Servo control and sensor fusion would be perhaps the primary concepts that one needs to know. You need to have industrial grade servo motors. You can essentially also buy cheaper servo motors, distance sensors and wires. You can find and buy breadboards, and so that you can prototype electronic uh, circuit boards, essentially all of the basic electronics components that one needs, and you'd be able to find that easily. And essentially once you start doing the project, you'll gain more and more clarity. And then software subsystem essentially involves implementing inverse kinematics for arm movement and object recognition algorithms as well, using C, C++. And essentially for hardware related projects, it makes sense to work with C++ because it is low level, and this is also what is primarily used in industries. Python is more widely used for machine learning and data science related projects. So you need a computer with ROS and C++ or compilers. So ROS is something that is used, very widely used as a standard in the industry. So this is something one needs to know. Then the second project is planetary drill simulator, and that involves creating a drilling system that can penetrate different layers of simulated planetary surface. Of course, this has to be also a miniaturized version, and it doesn't have to be full scale or to the same level of complexity as the real planetary drilling simulator. Just to give a sense of what a project like that involves. So to develop a drilling system capable of penetrating at least 3 different types of materials and provide real-time feedback, just to make it more specific, and the difficulty level is of course also um, 4 star is what I have given for this project, because it involves integration of a lot of different components. But of course it is doable within a year if one focuses on it for the number of hours that I've specified. And you have to design a mechanical subsystem for penetrating various materials like sand, clay, and rock. You need to know SolidWorks and CNC machine. So essentially, the tools are something that I've kept the same for the sake of simplicity, and so that one can focus on a few set of tools and really understand those better in a really good way. You need to know material science more for this project and mechanical design principles. You need to know have drill bits, mounting frame. Essentially, the hardware requirements are something that one can figure out on their own once they are really invested in the project, once they have really started defining the project and started doing the project. So electrical or electronic subsystems, you need to have stepper motors for drill rotation and force sensors for feedback. You need industrial grade stepper motors, force sensors, and wires. These are the requirements. The concepts that you need are, of course, stepper motor control and how sensor feedback works. For the software system, you have to implement a control algorithm to adjust the drilling speed based on sensor feedback using C++, and you need to know feedback control and data processing, and we'll be using ROS and C++ for this project. The third project is 3D printer with material recognition. Build a 3D printer that can recognize and adjust settings based on the material being used. You have to develop a 3D printer capable of recognizing at least three different types of printing materials and essentially adjusting its settings. And again, the project difficulty level is 4. Here, you require to build and assemble a 3D printer frame and an extruder. You need to know about assembly, which is probably something that is more practical, but you can also look at the theoretical aspects of mechanical design that involve assembly of components, material science, and then also aluminum frames, stepper motors, extruder assembly. So essentially, how would you assemble all those components together? And then electrical components involves integration of temperature and material sensors in this case, and you need to have temperature sensors, material sensors, control board, and you need to know sensor integration and circuit design. Again, these are maybe broad categories of concepts that one needs to know. Essentially, once you start defining your own project pipeline, you can and you start building it, you'd then be able to understand, okay, hey, I do not really know how to control stepper motors, for instance, for one project, or I do not really know how temperature sensors work. So you might need to then learn more. And essentially, the whole curriculum is designed to be project based and hands on, and you can only make progress and understand things once you start building it, get stuck, get frustrated, and then look up for theory to find missing pieces or gaps in your knowledge. And for software system, then develop a software to adjust print settings based on material recognition using C++. You can use machine learning and control algorithms for this. Autonomous lunar rover, build a small scale autonomous rover capable of navigating a simulated lunar surface. A lot of people have also built these small scale autonomous rover projects and shared their entire process of building it online. You can find articles on this. You can even find YouTube videos of people sharing how they built this project in a lot of detail. So this is something that can be easily found. So build a rover that can autonomously navigate a one by one area, avoiding obstacles, reaching specified waypoints. So this is something that involves a lot of different sensor integration, advanced software algorithms, and but you would essentially also learn a lot. And this is something, if you build it, you'd of course gain a really good pseudo real world experience, and that would essentially um, be look very good on your portfolio, and the companies would essentially value it a lot, especially because it shows that, hey, you took the initiative to build this project all by yourself. um, and if you have a good result to show, then companies would really appreciate that. Design and assemble a four-wheeled rover chassis. You can use again the same concepts and tools that one requires. You need to have certain hardware components that are required for the mechanical subsystem, and for electronics and electrical subsystems, you need to integrate GPS and obstacle avoidance sensors. So in this case, you need to know circuit design and sensor fusion. You need to have GPS modules, maybe even ultrasonic sensors and control boards. You can choose the kind of sensors based on your availability and your budget. Develop navigation algorithms and obstacle avoidance logic using C, C++. You would learn concepts such as path planning and sensor fusion and work with ROS and C++ compiler. So the fifth project is Satellite Docking Simulator, essentially a low-cost home-based simulator that can accurately mimic the docking properties of a satellite. So the scope of this project essentially depends on your time availability, the feasibility depending on the availability of hardware components and budget and a lot of different things. So this is just to give an idea of what are the different possible projects that you could invest in as a beginner. Mechanical subsystem is to build a miniature docking port and satellite model as simplified as you can make it. Use magnetic locks for docking, and you need to learn concepts about electromagnetism, magnetic locks, power supply, and more of these category of concepts in electrical and electronics engineering. You have to develop a control algorithm for autonomous docking using C, C++. The sixth project is Space Debris Collector, and you have to design a small scale model of a space debris collector that can autonomously collect at least three different sizes of simulated space debris. Design a net or claw mechanism for debris collection. This essentially also comes into mechanism and mechanical design, kinematics and dynamics that you would need to know for this case, and integrate cameras and proximity sensors for debris detection. And you need to know how to integrate cameras, proximity sensors, and use control board, sensor fusion, image processing, essentially also object detection, path planning, and even computer vision algorithms in this case. In-space refueling simulator, create a simulator for in-space refueling operations between a spacecraft and a refueling station to develop a simulator that demonstrate the docking, fuel transfer, and undocking process. Design a miniature spacecraft and refueling station with docking ports. You need to also know perhaps some fluid dynamics and CAE in this case. And I'll be sharing a book on mechanical design as well after I'm done sharing the projects in one of the later slides. So that book would be more than enough to really get started with building projects. And once you see that, hey, I need to know more specific concepts, and you can look up more uh, theory from other books or other lectures and videos and courses. You need to integrate flow sensors and locking mechanisms. So this is another different category of project, and you need to develop algorithms for autonomous docking, fuel transfer, and undocking. The eighth project is Spacecraft Thermal Control System Simulator, and you need to develop a simulator that can demonstrate the heating and cooling processes of the spacecraft's thermal control system. And this is also a slightly more complex project, and you need to design a miniature spacecraft project with thermal control elements like heat sinks and radiators. And you need to work with thermal sensors, heating elements, and control boards. And you need to design algorithms for autonomous thermal control using C++. Note that I have not specifically written which algorithm you would implement, because this is something that you have to do some literature survey on and find out what are the state of the art algorithms in the kind of domain that you are dealing with, and essentially um learn the theory by means of doing that literature survey and really then implement that algorithm. So that is why these projects are giving a really a high level description of what is expected to do, and the details and the project definition come essentially based on your own interest and defining your own scope. Ninth, and another interesting robotic arm project and a simpler project, is to develop a 2 degree of freedom robotic arm that can perform at least 5 different actions based on voice commands. So a simpler project as compared to the other ones. And you need to know, of course, kinematics and dynamics. In this case, you need to know audio signal processing, circuit board design, and you need to have a microphone amplifier and a control board. You need to work with speech recognition and natural language processing libraries in this case. And in this case, I mentioned C++ because we still are dealing with the hardware component, but you can also work with Python in this case. So the last project is Space Telescope Simulator. Maybe it's a very complex project, but it is something you should choose only if you're really in this area and you want to really explore this. You're really interested in this, and you follow this specific domain regularly. So to develop a simulator that can demonstrate the tracking, focusing, and data capture processes of a space telescope. So this project is highly interdisciplinary, involving all the different components that we mentioned, making it challenging but highly educational. And you have to design a miniature telescope with adjustable focus and orientation, integrate motors for orientation and a camera for capturing images. You need to know motion control, image capture, stepper motors, camera, control board, and develop algorithms for star tracking and image processing using C++. Again, this can be simplified to a certain degree depending on what areas or what parts of the project you really find interesting. Okay, so a typical project pipeline looks as follows, and this is essentially derived from the book Robert L. Norton, Design of Machinery by Robert L. Norton. And this is essentially about the analysis of mechanisms in machines, synthesis and analysis of mechanisms in machines, so about uh, kinematics primarily, but about machine design in general. And this can be applied even to interdisciplinary projects that deal with electronics and software components. So the overall process would be more or less same. So you first start with identifying the problem and gathering the project requirements and establishing constraints. So you have to really spend some time really defining the problem clearly. You have to do some background research, collect information, learn the theoretical concepts that you might need for the project. You have to develop concepts and sketches to create your initial model. This is also something that you have to do all by yourself, and this is something that is also one of the most exciting phases of any engineering project, because this is a creative activity and you get to create a lot of different concepts, and then you choose a concept based on certain design criteria and your constraints. Then you create detailed mathematical models of the chosen concepts, and these include kinematic and dynamic analysis. And you do feasibility analysis of the design concept by analyzing material cost, manufacturing processes, and other relevant factors. For more details, I highly encourage you to read the first few chapters of this book, where the process is defined in more detail. And there's also a lot of projects, I think, in the appendix, or at least the last chapter. Those projects are essentially mechanical design related based, but you can also find some interdisciplinary projects, or you can get some ideas about interdisciplinary projects which you can then uh, filter out and try to choose a few projects from that. So the next step is using CAE, computer aided engineering and computer aided design and manufacturing tools, to simulate the performance of the design, optimize the parameters for maximum efficiency and reliability, and develop a prototype to test the design first. So this is the first step in making something hands-on, to develop a virtual prototype to test the design. Then you conduct experiments and test to prototype on the prototype to validate the design and make necessary adjustments based on the results. Then you finalize the design specifications, including detailed drawings, parts lists, and manufacturing instructions. Again, this points to this is specifically coming from a mechanical engineering standpoint. That's why they talk about creating detailed designs and part lists and manufacturing instructions, but would also apply to, let's say, designing an electronic circuit or a PCB. So the next step is then implementation or moving to the manufacturing phase and building the final product. You may or may not want to do that here because you're still exploring and you can still just be there till the final design, so and add it to your portfolio, or even just a prototype that is really good enough to be demonstrated and be added to your resume and to your portfolio. And after that, you have to do quality control and monitoring and documentation and reporting. So these are optional steps, but these are typical steps in an industrial engineering project. Some points to consider. The goal of the list is to give you an idea of personal industry related projects in different domains in space robotics. You choose one of the projects based on your interest and feasibility and depending on the available resources, and it is absolutely okay to reduce the scope of the project to take into account your current skill set and your time availability. So you do not need to have any prerequisites. Choose a project of your interest and learn the theory along the way. This is, in any case, the best way to learn engineering. You can ask anyone who has a good level of engineering background, who has several years of engineering experience. They would all say that engineering is best learned by building projects and gaining practical experience. So the way I've designed this curriculum is I've created a single large interdisciplinary project, and that is what is specifically suitable for Daniel because he wanted to have a challenging project and he wanted to explore a lot of different domains. And so for this particular case, it makes sense. You can essentially also take up mini projects in multiple domains. So a mini project in mechanical design domain, and and a separate mini project in electronics, a separate mini project in, let's say, software navigation, uh, and any area of your interest, and really also try to figure out your niche in that way. But for this case, it makes more sense in my view to really try out a larger interdisciplinary project, and essentially this would be challenging and it may require even more than a year or slightly less than a year depending on your time availability. So make sure to find a group of people that can offer you accountability and support, and if you're doing it in a group, essentially you would learn and make progress faster because there are more people to contribute. You will also get the experience of how it is like working in an engineering team and building on engineering projects. So if this is a possibility for you, I highly recommend finding a group of people. Consider participating in competitions. In competitions, generally people participate in groups and you get some exposure as well. There are a lot of space engineering, space robotics related competitions out there. You can find that quickly by a quick Google search. So if that is a possibility, definitely consider it. So now coming on to defining your niche. Once you have built the mechanical subsystem, the electronic subsystem, and the computer or the software subsystem, then essentially you have gained enough exposure to really identify your strengths and values, the topics or projects of your interest, and what kind of tools you like to work with, and really define your niche. So you have to spend some time really identifying what are the things you value. Do you value learning, creativity, originality, excellence and efficiency, or growth, spontaneity, collaboration, teamwork, innovation? What are the things that you value? So this is something that you have to spend time really identifying for yourself. And then what are your strengths? This is something you cannot really answer for yourself without doing the project. Once you start doing the project, you can recognize that, hey, I like working with mechanical systems, and I'm also actually very efficient when I'm doing this. I can really come up with good designs very quickly. Maybe it is conceptual design that you're really good at. Maybe it is synthesis, or maybe it is finite element analysis. Maybe it is circuit board design. Maybe it is programming for you. So you have to also take your strengths into account, and essentially that would play a huge role in defining a proper meaningful career. You would be able to figure out your interests within the domain of space robotics once you do these interdisciplinary projects. Maybe you like mechanical design the most out of all these different domains, and that is good. Maybe you like deep learning, machine learning, computer vision more. Maybe you like electronics more. Maybe you want to do focus on robotic software engineering, but you like navigation domain the most. And another point that I've mentioned many times is that you have to choose projects that are at the intersection of your skills and challenge. So if you see that my skill level maybe in programming is not really that good, then you can take up a slightly easier project, and nothing wrong with that, and you would essentially be enjoying building that project because it is not too difficult and also not too easy. So you would probably experience flow states while you're doing that, and then you can slowly increase the difficulty. So now coming to the crux of the video, which is goal setting. So here's the aspiration of Daniel. These are the aspirations of Daniel. Daniel wants to pursue a master's in engineering in space applications. He wants to find out his niche in robotics, software, and hardware profiles, and he seeks a project based curriculum to essentially gain a foundation so that he can then also decide which is this specific domain he should pursue his master's in. And really, if he can figure out his niche in robotics, software, and hardware profile. So essentially, the plan goes like this. The first 2 months are essentially dedicated to project planning. So the first month, let's say if you choose to start uh, engaging with your learning from October, then the first month is dedicated to selecting a project, and I've talked about how to select a project. And I've given you a list of projects. So you have to select a project, you can think about it and consider your constraints into account and choose a project and create a detailed project pipeline. What would the mechanical subsystem look like? What would the electronic subsystem look like? What is the problem statement? Essentially, uh, the RL Norton project pipeline that I shared. And then you arrange the raw materials. Since this is also hardware related projects, you probably need to spend some time arranging the electronics, the mechanical components, maybe the 3D printer, depending on your project. So you would spend 1 month arranging all the raw materials, and then you would spend uh, the next 3 months building the mechanical subsystem, and you would spend 1 month or maybe a couple of weeks depending on how quickly you learn, and you can spend some time really getting familiar with SolidWorks and any other mechanical design tool, and then you would just spend your time building the mechanical system, and that process would be essentially very messy, where you're trying to build the system. You would get frustrated a lot, you would get stuck at certain problems, and then you can look up theory and then you can build things, and this is how a typical engineering project looks like. You would then spend the next 3 months building the electronic subsystems. Again, you learn the electronics basics, you learn LabVIEW, the basic uh, electronics tool that you would use, and then you spend the next 2 months building the electronics subsystem. And then essentially the next 3 months would be dedicated to building the software system. You learn ROS and C++, and even TensorFlow if you're using if you choose to go for machine learning in your project, and if you want to explore that. So you would build the software subsystem, and then the last month would be dedicated to really defining your niche. And I've talked about you have to define your strengths, what kind of impact that you want to have, and your areas of interest. And you can take up 1 month and really uh, think about the systems that you built. What was it that you really enjoyed doing more, and really try to organize the projects and build a portfolio of projects and come up with a conclusion. Fix one niche. You cannot be an expert in everything. You have to choose one area to gain expertise in. This whole experience would give you enough exposure to the three major subdomains in robotics, essentially, and then you can choose to specialize in one specific subdomain, and then you can even narrow down further once you've chosen a niche. So select a project pipeline, create a project, choose a project based on your interests. Don't spend too much time over analyzing and finding the perfect project topic. Just choose any project that you find interesting, because you would only gain exposure once you start doing it. And be open to updating the plan, because as you start doing it, you maybe would realize that some things take more time than expected, some things take less time than you had anticipated, and then you should be really open to updating the plan and not rigidly stick with a plan that you created. Learn SolidWorks, CATIA, or NX for 1 month. Define the mechanical problem statement clearly, follow the RL Norton project pipeline to create the plan, and start building the project and learn the theoretical concepts as needed. Start building the project and learn the theory as you start doing it. Likewise, same goes for building the electronic subsystem. And for software subsystem, essentially, you would choose to learn Python or C++, depending on um, your project. If it is a more data science or machine learning project, you can choose to go for Python, but in general C++ would be more relevant for at least a majority of the projects that I've mentioned, because these still involve hardware. So learn ROS and learn TensorFlow if it requires machine learning integration there. Define the software problem statement clearly, create a project pipeline, start building the project, and learn the theoretical concepts along the way. And as I mentioned, the choice of whether to learn ROS or not, whether to learn C, C++, or Python depends on the chosen project. For hardware projects, C, C++ is generally important, and for implementing machine learning, TensorFlow using Python is of primary significance. And you can watch my video titled The Most Comprehensive List of ROS2 Resources for Beginners to find a really good list of ROS2 resources if you want to learn ROS. Last month is dedicated to choosing a career niche. Essentially, you have to choose between one of these three, and once you have chosen that, maybe the next year could be dedicated to really narrowing down your niche if you still want to further refine it. But essentially, you would be clear on which of these three domains you are primarily interested in. So the weekly and daily goals are essentially the monthly goals split into four sub goals, and these should be flexible depending on um, what time you have. Maybe some of the weeks you have less time, and some of the weeks you have more time, so you can really adjust those. And in order to be accountable and stay consistent towards your learning and building goals, block 2 hours on the weekends, on the weekdays, and 4 hours on the weekends, and you can really use FocusMate to stay accountable. Some additional questions that would be relevant to Daniel for his specific scenario. So, how do you gauge the difficulty level of a project? A project is easy if your skill set matches or exceeds the challenge that the project offers, and then you experience boredom. So if a project is too easy and your skills are more than the challenge that the project offers, then you would not really be engaged that much, and that is also not good. A project is hard if the challenge exceeds your skill set, and then you would be overwhelmed, you'd get frustrated, you wouldn't know how to proceed, and you would not enjoy that process that much. So make sure to choose a project that is at the right that has a right balance of skills, your skill set, and the challenge that the project offers. The tools that are used by the industry are essentially PyTorch or TensorFlow for machine learning. TensorFlow is more used for industries, and PyTorch is generally preferred in research. OpenCV is the standard image processing or computer vision library. ROS or ROS2 is used for robotic software engineering positions. Gazebo is a common simulation platform for robotics positions. For research, PyBullet, Gojoko, and IsaacSim are used, which would probably not be relevant for Daniel. Which tools are relevant used by the industry? Essentially, look at the list of job profiles, and I've essentially done that for you in this curriculum. And this is an example of a job profile by Boston Dynamics AI Institute that essentially requires experience with either C++ or Python, or experience working with deep learning techniques in NLP and computer vision, and experience using data science tools, libraries, and frameworks such as scikit-learn, pandas, numpy, TensorFlow, etc. So this is very important. You have to choose to build the kind of projects, build projects that use the kind of tools that are used by the industry. How to apply to startups as a beginner, and if you're someone who is motivated to explore a lot of different domains, you get a lot of exposure um, to work on interdisciplinary projects and explore a lot of different areas by working in startups. You can find a list of companies in your niche from LinkedIn and job portals, and browse the official website of the companies in your area or wherever you're applying, and make a list of the skills that they require. Build projects, create a portfolio of projects, and feel free to also do an unsolicited application if there's no job opening in your domain. And lastly, here are some ROS resources that you can refer to. So that is it. I hope this curriculum helps. Let me know uh, what kind of videos do you really find most beneficial. I can specifically also target making videos on particular robotic applications, such as maybe a video on agricultural robotics in general, and a roadmap if you want to become an agricultural robotics engineer, or any other specific domain, let's say a machine learning or data science engineer for a medical application. So it depends on a lot of things. So it could be a lot of different videos, or it could be mini courses, or it could be tutorials on ROS, Python, TensorFlow, PyTorch, and a lot of different possibilities are there. So essentially, let me know what kind of videos you find the most beneficial. Hopefully this video was useful to you. So good luck to you.